Deep in the cosmos, between the clusters, galaxies, nebulae, lies a massive gravitational field that even light can't wait to enter. In deep lies a singularity which is now infinite dense and can sink any type of matter in it. It's none other than a black hole. First of all, the term black hole is not very ancient. It's a recent origin. It was coined by 1969 by an American scientist, John Wheeler, as a graphic description of his idea that goes back at least 2000 years ago. It was predicted in a time where people fought for a division. One of the group favored the Newtonian theory that light composed of particles, and the other group believed that light is consist of waves. However, we now know that both of the theories were correct, as by the wave-light duality of quantum mechanics, light can be regarded as both waves and particles. But under the theory that light is made up of waves, it was not clear that how it might respond to gravity. But if light is composed of particles, one might expect that it would respond to gravity in the same way planets and rockets respond. On this discussion, a paper was published by the Royal Society of London in which they pointed out something mesmerizing. They pointed out that a star has a sufficient, massive and compact duality which have a storage of gravitational field that even light could not escape. Any light emitted on the surface of the star would be grabbed by the star's gravitational attraction before it could get very far. Along with this, he also suggested that there must be a large number of stars like this, although we were not able to see them as light from them wouldn't reach us. I know you all must be in a bit dilemma that if we not, then what are these pictures that we are seeing on this video or everywhere else? Basically, they are just certain CGI pictures that posted to give certain idea. And if you really want to see a black hole, just close your eyes. Apparently, we can, however, still feel their gravitational attraction. Such objects as what we call black holes, because that is what they are, black voids in space. To understand how a black hole formed, we need to understand the life cycle of a star. A star is formed when a large amount of gas, especially hydrogen, starts collapsing in on itself due to its gravitational attraction. As it contracts, the atom of the gases collide with each other with more and more frequency and at greater and greater speed. Finally, the gas starts heating up. And eventually, the gas becomes so hot that when the hydrogen atoms now collide, they will no longer bounce off each other, but instead they collapse to form helium. The heat released in this reaction, which is like a controlled hydrogen bomb explosion, is what makes a star shine. And due to this additional heat, it starts making pressure of the heat and it stops contracting. This mechanism is a bit like a balloon. In the case of balloon, there is a balance in the pressure of air inside, which is trying to make the balloon expand, and the tension in the rubber is trying to make the balloon smaller. The star will remain stable like this for a long, with heat from a nuclear reaction balancing the gravitational attraction. Eventually, the star will run out. This is because the more hotter the star is, the more hotness it needs to balance. And the more hotter it is, the faster it will use up its fuel. Don't worry, our sun has probably got enough fuel for another 5,000 million years. But the more massive star can use up its fuel, it starts cooling off and so that it contracts. Along with this, an Indian cosmologist, Chandrasekhar, worked out that how big a star could be and still support itself against its own gravity after it had used up all its fuel. The idea was this, that when a star becomes so small, the matter particles get near to each other, with obviously their different velocities, which makes them move from each other, and so that it tends to make the star expand. Therefore, a star needs a balance between the gravitational attraction and the repulsion that arises from the exclusion principle, just as earlier where its gravity was balanced by heat. Chandrasekhar realized that there must be limit for the repulsion and so that the expansion that can be provided. This means that when the star got sufficient dense, the repulsion caused by the expulsion principle would be less than the attraction of gravity. He calculated that a cold star of more than about one half of its mass would not be able to support its own gravitational field. This mass is now known as Chandrasekhar limit. But whereas if a star's mass is less than the Chandrasekhar limit, it would eventually stop contracting and will settle down to a possible and final state as a white dwarf. We generally observe a large number of white dwarfs these days. But whereas if a star has a mass that is above the Chandrasekhar limit, it has a big problem with it. If they came to the end of their fuel, in some cases they may explode or they somehow manage to throw off their matter so that they can come below the Chandrasekhar limit and so that they can avoid the catastrophic gravitational collapse. But it's difficult to believe that this always happens, no matter how big the star is. How would it know that it has to lose weight? And even if star managed to lose enough mass to avoid collapse, what would happen if you add more mass to a white dwarf or a neutronian star to take over the limit? Would it collapse to infinite density? But it was generally believed that it is not possible for a star to collide in on itself. Now after all this, the position of star is like that. The gravitational field of star changes the paths of light rays for what they would have been formed. Now the light came with indicates the paths followed in space and time by flashes of lights emitted by their tips, and they are slightly inward near the surface, and light games become inward more. This makes it more difficult for light from the star to escape, and eventually when the star has shrunk to a certain critical radius, the gravitational field at its surface became so strong and the light cones are being inward so much that light can no longer escape. And according to the theory of relativity, nothing can travel faster than light. So that if light cannot escape, neither can anything else. Everything gets dragged by its gravitational field. So one has a set of events, a region of space from which it is not possible to escape to reach a distant observer. And this region is what we called black hole. It's a boundary that named as event horizon, and it consists of the paths of light rays that just failed to escape from the black holes. In order to understand that what would you see if you are watching a star collapsing to form a black hole, one has to remember that in the theory of relativity there is no absolute time. Each observer has its own measure of time, so the time for someone on a star would be different for that of someone at a distance because of its gravitational field. Now after seeing the whole journey of a star converting into the black hole, actually there is something even very interesting. According to Roger Penrose and Stephen Hawking, there must be a singularity that have infinite density and space's time curvature within the black hole. It is rather a big bang at the beginning. At this singularity, the laws of science and our ability to predict the future would break down. But however, any observer who remained outside the black hole would not be affected by this failure of predictability, because neither light nor any other signal could reach to the singularity. Or we can say that the singularity produced by the gravitational collapse occurs only in the places like black hole where there is a decently hidden from outside view by an event horizon. Strictly, this is what we call weak cosmic censorship hypothesis. It protects who remain outside the black hole from the consequences of the breakdown of predictability that occurs at the singularity. Hence, black holes are the only fairly small number of cases in the history of science in which the theory was developed in a great detail as a mathematical model before there was any observations that was correct. But unfortunately, it is nothing at all for the poor, unfortunate astronaut who just fall into a black hole. Indeed, it can be the main argument for the opponents of the black holes. But that's not enough for these giant black holes. Along with this, there are irregularities required to account for stars in galaxies who led to the formation of a significant number of primordial black holes clearly depends upon the detail of conditions in the early universe. Hence, if we are able to determine that how many primordial black holes are present, we would able to learn a lot about the early stages of this cosmos. Okay, now let's take a break from these giant and dangerous black holes. Meet you guys in the next one.